Unit 1. Some basic concepts of chemistry. Chemistry is the science of molecules and their transformations. It is the science not so much of 100 elements but of infinite variety of molecules that may be built from them. Roald Hoffman. Science can be viewed as a continuing human effort to systematize knowledge for describing and understanding nature. You have learned in your previous classes that we come across diverse substances present in nature and changes in them in daily life. Curd formation from milk, formation of vinegar from sugarcane juice on keeping for prolonged time, and rusting of iron are some examples of changes which we come across in many times in daily life. For the sake of convenience, science is subdivided into various disciplines: chemistry, physics, biology, geology, etc. The branch of science that studies preparation, properties, structure and reactions of material substances is called chemistry. Development of chemistry. Chemistry as we understand it today is not a very old discipline. Chemistry was not studied for its own sake, rather it came up as a result of search of two interested things. Number one, philosopher's stone or paras, which would convert all baser metals, example iron and copper, into gold. Number two, exiler of life, which would grant immortality. People in ancient India had already the knowledge of many scientific phenomena much before the advent of modern science. They applied that knowledge in various walks of life. Chemistry developed mainly in the form of alchemy and electrochemistry during 1300 to 1600 CE. Modern chemistry took place in 18th century Europe after few centuries of alchemical tradition which were introduced in Europe by the Arabs. Other cultures, especially the Chinese and the Indian, had their own alchemical traditions. These included much knowledge of chemical processes and techniques. In ancient India, chemistry was called as Rasayan Shastra, Ras Tantra, Ras Kriya or Ras Vidya. It included metallurgy, medicine, manufacture of cosmetics, glass dyes, etc. Systematic excavation at Mohenjo-daro in Sindh and Harappa in Punjab prove that the story of development of chemistry in India is very old. Archaeological findings show that the baked bricks were used in construction work. It shows the mass production of pottery, which can be regarded as the earliest chemical process, in which the materials were mixed, molded and subjected to heat by using fire to achieve desirable qualities. Remains of glazed pottery have been found in Mohenjo-daro. Gypsum cement has been used in the construction work. It contains lime, sand and traces of calcium carbonate. Harappans made fiancé, a sort of glass which was used in ornaments. They melted and forged a variety of objects from metals such as lead, silver, gold and copper. They improved the hardness of copper for making the artifacts by using tin and arsenic. A number of glass objects were found in Makshi in South India around 1000 to 900 BCE and in Hastinapur and Taxila in North India around 1000 to 200 BCE. Glasses and glazes were colored by addition of coloring agents like metal oxide. Copper metallurgy in India dates back to the beginning of Chalcolithic cultures in the subcontinent. There are much archaeological evidences to support the view that technologies for extraction of copper and iron were developed indigenously. According to Rig Veda, tanning of leather and dyeing of cotton were practiced during 1000 to 400 BCE. The gold cloths of the black polished ware of northern India could not be replicated and is still a chemical mystery. These wares indicate the mastery with which the clean temperature can be controlled. Kautilya's Arthashastra described the production of salt. A vast number of statements and material described in ancient Vedic literature can be shown to agree the modern scientific findings. Copper utensils, iron, gold, silver ornaments and terracotta discs and painted grey pottery have been found in many archaeological sites in North India. Susrut Samhita explain the importance of alkalis. The Charak Samhita mentions the ancient Indians who knew how to prepare sulfuric acid, nitric acid and oxides of copper, tin and zinc. The carbonates of lead and iron. Rasopanishada describes the preparation of gunpowder mixture. Tamil texts also describe the preparation of fireworks using sulfur, charcoal, saltpetre, that is potassium nitrate, mercury, camphor, etc. Nagarjuna was the great Indian scientist. He was a reputed alchemist, chemist and a metallurgist. His work Ras Tantra deals with the formation of mercury compounds. He has also discussed methods for the extraction of metals like gold, silver, tin and copper. A book, Rasnavam, appeared in 800 CE. It discusses the uses of various furnaces, ovens and crucibles for different purposes. It describes the methods by which metals could be identified by flame color. Chakrapani discovered mercury sulfide. The credit for inventing soap also goes to him. He used mustard oil and some alkalis as ingredient for making soap. Indians began making soaps in 18th century CE. Oil of erand and seeds of mahua plant and calcium carbonate were used for making soap. The paintings found on the wall of Ajanta and Ellora, which look fresh even after ages, testify a high level of science achieved in ancient India. Varah Mihir's Bharat Samhita is a sort of encyclopedia which was composed in 6th century CE. It informs about the preparation of glutinous materials to be applied on the wall and the roofs of houses and temples. It was prepared entirely from the extracts of various plants, fruits, seeds and barks, which were concentrated by boiling and then treated with various resins. It will be interesting to test such materials scientifically and assess them for use. A number of classical texts like Atharva Veda around 1000 BCE mentions some dye stuff. The material used were turmeric, madder, sunflower, orpiment, chaconical and lac. Some other substances having tinking property were Kamplika, Patanga and Jatuka. Varah Mihir's Bharat Samhita gives references to perfumes and cosmetics. Recipes for hair dyeing were made from plant like indigo and minerals like iron powder, black iron, steel and acidic extract of sour rice gruel. Gandhayuki describes the recipes for making scents, mouth perfumes, bath powders, incense and talcum powder. Paper was known to India in 17th century as account of Chinese traveler I Sing describes. Excavation at Taxila indicate that ink was used in India from the 4th century. Colors of ink were made from chalk, red lead and minimum. It seems that the process of fermentation was well known to Indians. Vedas and Kautilya's Arthashastra mentions about many types of liquors. Charak Samhita also mentions ingredients such as barks of plants, stems, flowers, leaves, woods, cereals, fruits, and sugarcane for making asavas. The concept that matter is ultimately built up of invisible building blocks appeared in India a few centuries BCE as a part of philosophical speculations. Acharya Kanad, born in 600 BCE, originally known by the name Kashyap, was the first proponent of atomic theory. He formulated the theory of very small indivisible particles which he named Parmanu, comparable to atoms. He authored the text Vishesh Sutras. According to him, all substances are aggregated form of smaller units called atoms or Parmanu, which are eternal, indestructible, spherical, suprasensible and in motion in original state. He explained that this individual entity cannot be sensed through any human organ. Kanad added that there are varieties of atoms that are as different as the different classes of substances. He said these Parmanu could form pairs or triplets among other combinations and unseen forces cause interaction between them. He conceptualized this theory around 2500 years before John Dalton. Charak Samhita is the oldest Ayurvedic epic of India. It described the treatment of diseases. The concept of reduction of particle size of metal is clearly discussed in Charak Samhita. Extreme reduction of particle size is termed as nanotechnology. Charak Samhita described the use of bhasma of metals in treatment of ailments. Nowadays, it has been proved that bhasmas have nanoparticles of metals. After the decline of alchemy, electrochemistry reached a steady state, but it too declined due to the introduction and practice of Western medicine in 20th century. During this period of stagnation, pharmaceutical industry based on Ayurveda continued to exist, but it too declined gradually. It took around 100 to 150 years for Indians to learn and adopt new techniques. During this time, foreign products poured in. As a result, indigenous traditional techniques gradually declined. Modern science appeared in Indian scene in the later part of 19th century. By the mid-19th century, European scientists started coming to India and modern chemistry started growing. From the above discussion, you have learned that chemistry deals with composition, structure, properties and interaction of matter and is of much use of human beings in daily life. These aspects can be best described and understood in terms of basic constituent of matter that are atoms and molecules. That is why chemistry is also called the science of atoms and molecules. Can we see, weigh or perceive these entities, that is atoms and molecules? Is it possible to count the number of atoms and molecules in a given mass of matter and the quantitative relationship between the mass and the number of these particles? We will get the answer of some of these questions in this unit. We will further describe how physical properties of matter can be quantitatively described using numerical values with suitable units. 1.1. Importance of chemistry. Chemistry plays a central role in science and often intertwined with other branches of science. Principles of chemistry are applicable in diverse areas such as weather patterns, functioning of brain and operation of a computer, production of chemical industries, manufacturing fertilizer, alkali, acids, salts, dyes, polymers, drugs, soaps, detergents, metals, alloys, etc., including new materials. Chemistry contributes in a big way to national economy. It also plays an important role in meeting human needs for food, healthcare products, and other material aimed at improving the quality of life. This is exemplified by a large-scale production of varieties of fertilizer, improved variety of pesticide and insecticide. Chemistry provides methods for the isolation of life-saving drugs from natural sources and makes possible synthesis of such drugs. Some of these drugs are cisplatin and taxol, which are effective in cancer therapy. The drug AZT, that is azithromycin, is used for helping AIDS patients. Chemistry contributes to a large extent in the development and growth of a nation. With a better understanding of chemical principle, it is now become possible to design and synthesize new material having specific magnetic, electric, and optical properties. This had led to the production of superconducting ceramics, conducting polymers, optical fibers, etc. Chemistry has helped in establishing industries which manufacture utility goods like acids, alkalis, dyes, polymer metals, etc. These industries contribute in a big way to economy of the nation and generate employment. In recent years, chemistry has helped in dealing some of the pressing aspects of environmental degradation with a fair degree of success. Safer alternatives to environmentally hazardous refrigerants like CFCs or chlorofluorocarbons responsible for the ozone depletion in stratosphere have been successfully synthesized. However, many big environmental problems continue to matter of grave concern to the chemists. One such problem is the management of greenhouse gases like methane, carbon dioxide, etc. Understanding to the biochemical processes use of enzyme for large-scale production of chemicals and synthesis of new exotic material are some of the intellectual challenges for the future generation of chemists. A developing country like India needs talented and creative chemists for accepting such challenges. To be a good chemist and to accept the challenges, one needs to understand the basic concepts of chemistry, which begin with the concept of matter. Let us start with the nature of matter. 1.2 Nature of matter. You are already familiar with the term matter from your earlier classes. Anything which has mass and occupies space is called matter. Everything around us, for example, book, pen, pencil, water, air, and all living beings, etc., are composed of matter. You know that they have mass and they occupy space. Let us recall the characteristic of states of matter which you have learned in previous classes. 1.2.1 States of matter. You are aware that matter can exist in three physical states, which is solid, liquid, and gases. The constituent particles of matter in these three states can be represented as shown in figure 1.1. Particles are held very close to each other in solids in an orderly fashion and there is not much freedom of movement. In liquids, the particles are close to each other but they can move around. However, in gases, the particles are far apart as compared to those present in solid or liquid states and their movement is easy and fast. Because of such arrangement of particles, different states of matter exhibit the following characteristics. Number 1. Solid have definite volume and definite shape. Number 2. Liquids have volume but do not have definite shape. They take shape of the container in which they are placed. Number 3. Gases. Gases have neither definite volume nor definite shape. They are completely occupy the space in the container in which they are placed. These three states of matter are interconvertible by changing the conditions of temperature and pressure. On heating, a solid usually changes to liquid and the liquid on further heating changes to gas or vapor. In the reverse process, a gas on cooling liquefies to liquid and the liquid on further cooling freezes to the solid. 1.2.2 Classification of matter. In class 11 chapter 2 you have learned that at macroscopic or bulk level matter can be classified as mixture or pure substance. These can be further subdivided as shown in figure 1.2. When all chemical constituent particles of substance are same in chemical nature, it is said to be a pure substance. A mixture contains many types of particles. A mixture contains particles of two or more pure substance which may be present in it in any ratio. Hence their composition is variable. Pure substances forming the mixture are called its component. Many of the substances present around us are a mixture. For example, sugar solution in water, air, tea, etc. are all mixture. A mixture may be homogeneous or heterogeneous. In a homogeneous mixture, the components completely mixes with each other. This means particles of the components of the mixture are uniformly distributed throughout the bulk of the mixture and its composition is uniform throughout. Sugar solution and air are the example of homogeneous mixture. In contrast to this, in a heterogeneous mixture, the composition is not uniform throughout and sometimes different components are visible. For example, mixtures of salt and sugar grains and pulses along with some dirt, often stone pieces, are heterogeneous mixture. You can think of many more examples of mixtures which you come across in daily life. It is worthwhile to mention here that the components of a mixture can be separated by using physical methods such as simple hand picking, filtration, crystallization, distillation, etc. Pure substances have characteristics different from mixture. Constituent particles of pure substances have fixed composition. Copper, silver, gold, water and glucose are some examples of pure substances. Glucose contains carbon, hydrogen and oxygen in a fixed ratio and its particles are of same composition. Hence, like all other pure substances, glucose have fixed composition. Also, its constituents carbon, hydrogen and oxygen cannot be separated by simple physical methods. Pure substances can further be classified into elements and compounds. Particles of an element consist of only one type of atoms. These particles may exist as atoms or molecules. You may be familiar with the concept of atoms and molecules from the previous classes. However, you will study about them in detail in Unit 2. Sodium, copper, silver, hydrogen, oxygen, etc. are some examples of elements. Their all atoms are of one type. However, the atoms of different elements are different in nature. Some elements such as sodium or copper contains atom as their constituent particles, whereas in others, the constituent particles are molecules which were formed by two or more atoms. For example, hydrogen, nitrogen and oxygen gases consist of molecules in which two atoms combines to give their respective molecules. This is illustrated in figure 1.3. When two or more atoms of different elements combine together in a definite ratio, the molecule is called compound is obtained. Moreover, the constituent of a compound cannot be separated into simpler substances by physical methods. They can be separated by chemical methods. Examples of some compounds are water, ammonia, carbon dioxide, sugar, etc. The molecules of water and carbon dioxide are represented in figure 1.4. Note that water molecule comprises two hydrogen atoms and one oxygen atoms. Similarly, a molecule of carbon dioxide contains one oxygen atom and combined with one carbon atom. Thus, the atoms of different elements are present in compound in a fixed or definite ratio, and this ratio is characteristic of particular compound. Also, the properties of a compound are different from those of its constituent elements. For example, hydrogen and oxygen are gases, whereas the compound formed by their combination, that is water, is a liquid. It is interesting to note that hydrogen burns with a pop sound and oxygen is a supporter of combination, but water is used as fire extinguisher. 1.3 Properties of matter and their measurement. 1.3.1 Physical and chemical properties. Every substance has unique or characteristic properties. These properties can be classified into two categories: physical properties such as color, odor, melting point, boiling point, density, etc. and chemical properties like composition, combustibility, reactivity with acids and bases, etc. Physical properties can be measured or observed without changing the identity or composition of the substance. The measurement or observation of chemical properties requires a chemical change to occur. Measurement of physical properties do not require the occurrence of chemical change. The examples of chemical properties are characteristic reactions of different substances. These include acidity, basicity, or combustibility, etc. Chemists describe, interpret, and predict the behavior of substances on the basis of their knowledge of physical and chemical properties, which are determined by the careful measurement and experimentation. In the following section, we will learn about the measurement of physical properties. 1.3.2 Measurement of physical properties. Quantitative measurement of properties is required for scientific investigation. Many properties of matter such as length, area, volume, etc. are quantitative in nature. Any quantitative observation or measurement is represented by number followed by units in which they are measured. For example, length of a room is represented as 6 meter. Here 6 is the number and m denotes meter, the unit in which the length is measured. Earlier, two different systems of measurement, that is the English system and the metric system, were used in different parts of the world. The metric system, which originated in France in late 18th century, was more convenient as it was based on the decimal system. Lately, need of a common standard was felt by the scientific community. Such a system was established in 1960 and is discussed in detail in below. 1.3.3 The International System of Units, or SI. The International System of Units in France, Les Systèmes International d'Unités, abbreviated as SI, was established by the 11th General Conference on Weights and Measures, or CGPM. The CGPM is an intergovernmental treaty organization created by diplomatic treaty known as Meter Convention, which was signed in Paris in 1875. The SI system has 7 base units and they are listed in table 1.1. These units pertain to 7 fundamental scientific quantities. The other physical quantities such as speed, volume, density, etc. can be derived from these quantities. Table 1.1. For length, the unit is meter and symbol is m. Mass, kilogram. Time, second. Electric current, ampere. Thermodynamic temperature, Kelvin. Amount of substance, mole. Luminous intensity, candela. The definitions of the SI units are given in table 1.2. The SI system allows the use of prefixes to indicate the multiple and submultiples of unit. These prefixes are listed in table 1.3. Let us now quickly go through some of the quantities which you will learn often using the book. Unit of length is meter. The meter is the length of the path travelled by light in vacuum during the time interval of 1/3 lakh of a second. Unit of mass is kilogram. The kilogram is the unit of mass. It is equal to the mass of the international prototype of kilogram. Unit of time is second. The second is the duration of 919263177 periods of radiation corresponding to the transition between two hyperfine levels of the ground state of cesium-133 atom. Unit of current is ampere. The ampere is the constant current which, if maintained in two straight parallel conductors of infinite length of negligible cross section and placed 1 meter apart in vacuum, would produce between these conductors a force equal to 2 × 10 inverse 7 Newton per meter of length. Unit of thermodynamic temperature is Kelvin. The Kelvin, the unit of temperature, is the fraction of 1/273.16 of the thermodynamic temperature of triple point of water. Unit of amount of substance is mole. Number 1. The mole is the amount of substance of system which contains as many elementary entities as there are in 0.012 kg of carbon-12. Its symbol is mole. Number 2. When mole is used, the elementary entities must be specified, and these may be atoms, molecules, ions, electrons, other particles, or other specified group of such particles. Unit of luminous intensity is candela. The candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 × 10⁻12 Hz and that has a radiant intensity in the direction of 1/683 watt per steradian. Table 1.3. Prefixes used in SI system. Tan inverse 24 yocto, tan inverse 21 japto, tan inverse 18 atto, tan inverse 15 femto, tan inverse 12 pico, tan inverse 9 nano, tan inverse 6 micro, tan inverse 3 milli, tan inverse 2 centi, tan inverse 1 deci, 10 deca, 10 to the power 2 hecto, 10 to the power 3 kilo, 10 to the power 6 mega, 10 to the power 9 giga, 10 to the power 12 tera, 10 to the power 15 peta, 10 to the power 18 exa, 10 to the power 21 jetta, 10 to the power 24 iota. 1.3.4 Mass and weight. Mass of a substance is the amount of matter present in it, while weight is the force exerted by the gravity on an object. The mass of a substance is constant, whereas its weight varies from one place to another due to change in gravity. You should be careful in using these terms. The mass of substance can be determined accurately in the laboratory by using an analytical balance. Figure 1.5. The SI unit of mass is given in table 1.1 is kilogram. However, its fraction named as gram, 1 kilogram equals 1000 gram, is used in laboratories due to smaller amounts of chemicals used in the chemical reaction. 1.3.5 Volume. Volume is the amount of space occupied by a substance. It has the SI unit of length to the power cube. So in SI system, volume of unit is meter cube. But again, in chemistry laboratory, smaller volumes are used, hence the volume is often denoted as centimeter cube or decimeter cube units. A common unit, liter, which is not an SI unit, is used for the measurement of volume of liquid. 1 liter equals 1000 ml. 1 decimeter cube equals 1000 centimeter cube. Figure 1.6 helps to visualize these relations. In the laboratory, the volume of liquids or solutions can be measured by graduated cylinder, burette, pipette, etc. A volumetric flask is used to prepare a known volume of solution. These measuring devices are shown in figure 1.7. 1.3.6 Density. The true properties mass and volume discussed above are related as follows. Density equals mass upon volume. Density of a substance is its amount of mass per unit volume. So the SI unit of density can be obtained as follows. SI unit of density equals SI unit of mass upon SI unit of volume equals kg per meter cube. The unit is quite large and a chemist often express density in grams per centimeter cube, where mass is expressed in gram and volume is expressed in centimeter cube. Density of a substance tells us how closely its particles are packed. If density is more, it means particles are more closely packed. 1.3.7 Temperature. There are three common scales to measure temperature: degree Celsius, degree Fahrenheit, and Kelvin. Here K is the SI unit or Kelvin is the SI unit. The thermometers based on these scales are shown in figure 1.8. Generally, the thermometer with the Celsius scale are calibrated from 0 to 100 degree, where these two temperatures are freezing and the boiling point of water respectively. The Fahrenheit scale is represented between 32 degree and 212 degree. The temperature on two scales are related to each other by the following relationship: degree Fahrenheit equals 9 upon 5 degree Celsius plus 32. The Kelvin scale is related to Celsius as follows: Kelvin equals degree Celsius plus 273.15. It is interesting to note that temperature below 0 degree Celsius, that is negative values, are possible in Celsius scale, but in Kelvin scale, negative temperature is not possible. 1.4 Uncertainty in measurement. Many a time in study of chemistry, one has to deal with experimental data as well as theoretical calculations. There are meaningful ways to handle the numbers conveniently and present the data realistically and certainly to the exact possible. These ideas are discussed below in detail. 1.4.1 Scientific Notation. As chemistry is the study of atoms and molecules which are extremely low masses and are present in extremely large numbers, a chemist has to deal with numbers as large as 602, 200 and 10 times 0 for the molecules of 2 gram of hydrogen gases, or as small as 0.00 and 12 times zeros after 166 gram mass of hydrogen atom. Similarly, other constants such as Planck's constants, speed of light, charge on particle, etc. involve numbers of above magnitude. It may look funny for the moment to write or count numbers involving so many zeros, but it offers a real challenge to do simple mathematical operations of addition, subtraction, multiplication or division with such numbers. You can write any two numbers from the above type and try any one of the operation like you to accept as challenge, and then you will really appreciate the difficulty in handling such numbers. This problem is solved by using the scientific notation for such numbers, that is exponential notation, in which any numbers can be represented in form of n into 10 to the power n, where small n is the exponent having positive or negative values and capital N is the number called digit term, which varies from 1.000 to 9.999. Thus we can write 232.508 as a 2.32508 into 10 to the power 2 in scientific notation. Note that while writing it, the decimal had to be moved to the left by 2 places, and the same is the exponent, that is 2, of 10 in scientific notation. Similarly, 0.00016 can be written as 1.6 into 10 inverse 4. Here the decimal has to be moved 4 places to the right, and minus 4 is the exponent in the scientific notation. While performing mathematical operations on numbers expressed in scientific notations, the following points are to be kept in mind. Multiplication and division. These two operations follow the same rule, which are therefore exponential numbers, that is 5.6 into 10 to the power 5 into 6.9 into 10 to the power 9 equals 3.864 into 10 to the power 14. 2.7 into 10 inverse 3 divided by 5.5 into 10 to the power 4 equals 4.909 into 10 inverse 8. Addition and subtraction. For these two operations, first the numbers are written in such a way that they have same exponent. After that, the coefficient, that is digit terms, are added or subtracted as in the case may be. Thus, for adding 6.65 into 10 to the power 4 and 8.95 into 10 to the power 3, exponent is made same for both the numbers. Thus, we get 6.65 into 10 to the power 4 plus 0.895 into 10 to the power 4, and then we get 7.545 into 10 to the power 4. Similarly, the subtraction of these numbers can be done as shown below. 1.4.2 Significant figures. Every experimental measurement has some amount of uncertainty associated with it because of limitation of measuring instrument and the skill of the person making the measurement. For example, mass of an object is obtained using the platform balance and it comes out to be 9.4 gram. On measuring the mass of this object on analytical balance, the mass obtained is 9.4213 gram. The mass obtained by an analytical balance is slightly higher than the mass obtained using the platform balance. Therefore, digit 4 placed after decimal in the measurement by platform balance is uncertain. The uncertainty in the experimental or calculated values is indicated by mentioning the numbers of the significant figures. Significant figures are meaningful digits which are known with certainty plus 1, which is estimated or uncertain. The uncertainty is indicated by writing the certain digits and the last uncertain digit. Thus, if we write a result of 11.2 milliliter, we say 11 is certain and 2 is uncertain, and the uncertainty would be plus minus 1 in the last digit. Unless otherwise stated, an uncertainty of plus minus 1 in the last digit is always understood. There are certain rules for determining the number of significant figures. These are stated below. Number 1. All non-zero digits are significant. For example, in 285 centimeter there are 3 significant figures, and in 0.25 milliliter there are 2 significant figures. Number 2. Zeros preceding to the first non-zero digits are non-significant. Such zero indicates the position of the decimal point. Thus, 0.003 has one significant figure and 0.0052 has 2 significant figures. Number 3. Zero between two non-zero digits are significant. Thus, 2.005 has 4 significant figures. Number 4. Zeros at the end or right of a number are significant, provided they are on the right side of the decimal point. For example, 0.200 gram has 3 significant figures, but if otherwise, the terminal zeros are not significant if there is no decimal point. For example, 100 has only one significant figure, but 100 point has 3 significant figures and 100.0 has 4 significant figures. Such numbers are better represented in scientific notation. We can express the number 100 as 1 into 10 to the power 2 has 1 significant figure, 1.0 into 10 to the power 2 has 2 significant figures, and 1.00 into 10 to the power 2 has 3 significant figures. Number 5. Counting the numbers of objects. For example, 2 balls or 20 eggs have infinite significant figures, as these are exact numbers and can be represented by writing infinite numbers of zeros after placing the decimal, that is 2 equals 2.10 times 0 or 20 equals 20.20 times 0. In numbers written in scientific notation, all digits are significant. Example, 4.01 into 10 to the power 2 has 3 significant figures, and 8.256 into 10 inverse 3 has 4 significant figures. However, one would always like the results to be precise and accurate. Precision and accuracy are often referred to while we talk about measurement. Precision refers to the closeness of various measurements for same quantity. However, accuracy is the agreement of particular value to the true value of the result. For example, if the true value of the result is 2.00 gram and the student A takes 2 measurement and reports results as 1.95 gram and 1.93 grams, these values are precise as they are very close to each other but not accurate. Another student B repeats the experiment and obtains 1.94 gram and 2.05 gram as the results of 2 measurements. These observations are neither precise nor accurate. When the third student C repeats these agreements, the reports are 2.01 gram and 1.99 gram as the result. These values are both precise and accurate. This can be more clearly understood from the data given in table 1.4. Addition and subtraction of significant figure. The results cannot have more digits to the right of the decimal point than either of the original numbers. Here 18.0 has only one digit after the decimal point and the result should be reported only up to one digit after the decimal point, which is 31.1. Multiplication and division of significant figure. In these operations, the result must be reported with no significant figures as in the measurement with few significant figures. 2.5 into 1.25 equals 3.125. Since 2.5 has two significant figure and the result should not have more than two significant figure, thus it is 3.1. While limiting the results to required number of significant figure as done in the above mathematical operation, one has to keep in mind in the following points for rounding of these figures. Number 1. If the rightmost digit to be removed is more than 5, the preceding number is increased by 1. For example, 1.386, if we have to be removed 6, we have to round it to 1.39. Number 2. If the rightmost digit to be removed is less than 5, the preceding number is not changed. For example, 4.334. If the 4 is to be removed, then the result is rounded off up to 4.33. Number 3. If the rightmost digit to be removed is 5, then the preceding number is not changed if it is an even number, but it is increased by 1 if it is an odd number. For example, if 6.35 is to be rounded by removing 5, we have to increase 3 to 4 by giving 6.4 as the result. However, if 6.25 is to be rounded off, it is rounded off to 6.2. 1.4.3. Dimensional analysis. Often while calculating, there is a need to convert unit from one system to another. The method used to accomplish this is called factor level method or unit factor method or dimensional analysis. This is illustrated below. Example, a piece of metal is 3 inch represented by IN long. What is the length in centimeter? Solution. We know that 1 inch equals 2.54 centimeter. For this equivalence, we can write 1 inch upon 2.54 equals 1 equals 2.54 upon 1 inch. Thus 1 inch upon 2.54 equals 1 and 2.54 upon 1 inch also equals 1. Both of these are unit factors. If some number is multiplied by these unit factors, that is 1, it will not be affected otherwise. Say the 3 inch given above is multiplied by the unit factor, so 3 inch equals 3 into 2.54 centimeter upon 1 inch equals 3 into 2.54 centimeter equals 7.62 centimeter. Now the unit factor by which the multiplication is to be done is that unit factor 2.54 upon 1 inch in the above case gives the desired results or desired units, that is, the numerator should have that part which is required in the desired result. It should also be noted in the above example that the units can be handled just like other numerical part. It can be cancelled, divided, multiplied, squared, etc. Let us study with one more example. A jug contains 2 liters of milk. Calculate the volume in meter cube. If you do the calculations, then 2 liters equals 2 into 1000 centimeter cube or 2 into 10 inverse 3 meter cube. Example, how many seconds are there in 2 days? Solution, 1,72,800 seconds. 1.5. Law of chemical combination. The combination of elements to form compound is governed by following 5 basic laws. 1.51. Law of conservation of mass. This law was put forth by Antoine Lavoisier in 1789. He performed careful experimental studies for combustion reactions and reached to the conclusion that in all physical and chemical changes there is no net change in masses during the process. Hence he reached to the conclusion that matter cannot be created nor be destroyed. This is called as law of conservation of mass. This law formed the basis of several later developments in chemistry. In fact, this was the result of exact measurement of masses of reactants and products and carefully planned experiments performed by Lavoisier. 1.5.2. Law of definite proportions. This law was given by a French chemist, Joseph Proust. He stated that a given compound always contains exactly the same proportion of elements by weight. Proust worked on 2 samples of cupric carbonate, one of which was natural origin and other was synthetic. He found that the composition of element present in it was same for both the samples as shown in below. Thus, he concluded that irrespective of the source, a given compound always contains same element combined together in same proportion by mass. The validity of this law was confirmed by various experiments. It is sometimes also to be referred as law of definite composition. 1.5.3 Law of multiple proportions. This law was proposed by Dalton in 1803. According to this law, if two elements can combine to form more than one compound, the masses of one element that combine with the fixed mass of other element are in the ratio of small whole numbers. For example, hydrogen combines with oxygen to form two compounds, namely water and hydrogen peroxide. Hydrogen of 2 gram and water of 16 gram gives water of 18 gram. Hydrogen of 2 gram and oxygen of 32 gram makes hydrogen peroxide of 32 grams. Here the masses of oxygen, that is 16 gram and 32 gram, which combine with the fixed masses of hydrogen, that is 2 gram, bear a simple ratio of 16:32 or 1:2. 1.5.4 Gay-Lussac's law of gaseous volumes. This was given by Gay-Lussac in 1808. He observed that when gases combine or are produced in a chemical reaction, they do so in a simple ratio by volume, provided all gases are at same temperature and pressure. Thus, 100 ml of hydrogen combined with 50 ml of oxygen to give 100 ml of water vapor. Thus, the volume of hydrogen and oxygen which combine, that is 100 ml and 50 ml, bear a simple ratio of 2:1. Gay-Lussac's discovery of integral ratio in volume relationship is actually the law of definite proportions by volume. The law of definite proportion stated earlier was respect to mass. The Gay-Lussac's law was explained properly by the work of Avogadro in 1811. 1.5.5 Avogadro's law. In 1811, Avogadro proposed that equal volume of all gases at same temperature and pressure should contain equal number of molecules. Avogadro made a distinction between atom and molecule, which is quite understandable in present time. If we consider again the reactions of hydrogen and oxygen to produce water, we see that two volumes of hydrogen combine with one volume of oxygen to give two volumes of water without leaving any unreacted oxygen. Note that in figure 1.9, page number 66, each box contains equal number of molecules. In fact, Avogadro could explain the above result by considering the molecules to be polyatomic. If hydrogen and oxygen were considered as diatomic as recognized now, then the above results are easily understandable. However, Daltons and others believed at that time that atoms of the same kind cannot combine, and molecules of oxygen and hydrogen containing two atoms did not exist. Avogadro's proposal was published in French journal de Physique. In spite of being correct, it did not gain much support. After about 50 years, in 1860, the first international conference on chemistry was held in Karlsruhe, Germany, to resolve various ideas. At the meeting, Cannizzaro presented a sketch of a course of chemical philosophy which emphasized on the importance of Avogadro's work. 1.6 Dalton's atomic theory. Although the origin of the idea that matter is composed up of small indivisible particles called atomio, meaning indivisible, dates back to the time of Democritus, a Greek philosopher, it again started emerging as a result of several experimental studies which led to the laws mentioned above. In 1808, Dalton published a new system of chemical philosophy in which he proposed the following. Number 1, matter consists of indivisible atoms. Number 2, all atoms of a given element have identical properties including identical mass. Atoms of different elements differ in mass. Number 3, compounds are formed when atoms of different elements combine in a fixed ratio. Number 4, chemical reactions involve reorganizations of atoms. These are neither created nor destroyed in a chemical reaction. Dalton's atomic theory could explain the law of chemical combination. However, it could not explain the law of gaseous volumes. It could not provide the reason for combining of atoms, which was answered later by other scientists. 1.7 Atomic and molecular mass. After having some idea about the terms atoms and molecules, it is appropriate here to understand what do we mean by atomic and molecular masses. 1.7.1 Atomic mass. The atomic mass or mass of an atom is actually very small because atoms are extremely small. Today we have sophisticated techniques, example mass spectrometry, for determining the atomic masses fairly accurately. But in 19th century, scientists could determine the mass of one atom relative to another by experimental means, as has been mentioned earlier. Hydrogen, being the lightest atom, was arbitrarily assigned a mass of 1 without any units, and other elements were assigned mass relative to it. However, the present system of atomic masses is based on carbon-12 as standard and has been agreed upon in 1961. Here, carbon-12 is one of the isotopes of carbon and can be represented as C12. In this system, C12 is assigned a mass unit of exactly 12 atomic mass unit or AMU, and the masses of all other atoms are given relative to this standard. One atomic mass unit is defined as the mass exactly equal to 1/12th mass of one carbon-12 atom, and 1 AMU equals 1.66056 into 10 inverse 24 gram. Mass of an atom of hydrogen equals 1.67 into 10 inverse 24 gram. Thus, in terms of AMU, the mass of an hydrogen atom equals 1.008 AMU. Similarly, the mass of oxygen 16, that is O16 atom, would be 15.995 AMU. At present, AMU has been replaced by U, which is known as unified mass. When we use atomic masses of elements in calculation, we actually use the average atomic masses of element, which are explained below. 1.7.2 average atomic mass. Many naturally occurring elements exist as more than one isotope. When we take into account the existence of these isotopes and their relative abundance, that is percent occurrence, the average atomic mass of an element can be computed. For example, carbon has 3 following isotopes with relative abundances and masses shown against each of them. From the above data, the average atomic mass of carbon will come out to be 0.98892 into 12 unit plus 0.01108 into 13.003 unit plus 2 into 10 inverse 12 into 14.00317 unit equals 12.001 unit. Similarly, the average masses of other elements can be calculated. The periodic table of elements, the atomic masses mentioned for different elements actually represent their average atomic masses. 1.7.3 Molecular mass. Molecular mass is the sum of atomic masses of elements present in a molecule. It is obtained by multiplying the atomic mass of each element by the number of its atom and adding them together. For example, molecular mass of methane, which contains 1 carbon atom and 4 hydrogen atom, can be obtained as molecular mass of methane equals 12.001 unit into 1 plus 4 into 1.008 unit equals 16.043 unit. Similarly, molecular masses of water, that is H2O, equals 2 into atomic mass of hydrogen plus 1 into atomic mass of oxygen equals 2 into 1.008 unit plus 16.00 unit equals 18.02 unit. 1.7.4 Formula mass. Some substances such as sodium chloride do not contain discrete molecules as their constituent unit. In such compound, positive, that is sodium ion, and negative, that is chloride ion, entities are arranged in 3-dimensional structure as shown in figure 1.10. It may be noted that sodium chloride 1 Na plus ion is surrounded by 6 Cl minus ion and vice versa. The formula such as NaCl is used to calculate the formula mass instead of molecular masses, as in the solid state sodium chloride does not exist as a single entity. Thus, the formula mass of sodium chloride is atomic mass of sodium plus atomic mass of chlorine equals 23.0 unit plus 35.5 unit equals 58.5 unit. Now here is a problem, just pause the video and solve it. 1.8 Mole concept and molar masses. Atoms and molecules are extremely small in size, and their number in even a small amount of substance is really very large. To handle such a large number, a unit of convenient magnitude is required. Just as we donate 1 dozen for 12 item, score for 20 item, cross for 144 item, we use the idea of mole to count the entities at a microscopic level, that is atoms, molecules, particles, electrons, ions, etc. In SI system, mole was introduced as 7th base quantity for the amount of substance. 1 mole is the amount of substance that contains as many as or entities as there are atoms in exactly 12 gram or 0.012 kg of carbon-12 isotope. It may be emphasized that the mole of a substance always contains same number of entities no matter what the substance may be. In order to determine this number precisely, the number of carbon-12 atom was determined by mass spectrometer and found to be equal to 1.99 into 10 inverse 23 gram. Knowing that 1 mole of carbon weighs 12 gram, the number of atoms in it is equal to 12 per mole carbon-12 upon 1.992648 into 10 inverse 23 equals 6.022 into 10 to the power 23 atoms per mole. This number of entities in 1 mole is so important that it is given a separate name and symbol. It is known as Avogadro constant or Avogadro number, denoted by Na in honor of Amedeo Avogadro. To appreciate the largeness of this number, let us write all the zero without any power of 10. Hence, so many entities, atoms, molecules or any other particle constitute 1 mole of particular substance. We can therefore say 1 mole of hydrogen equals 6.022 into 10 to the power 23 atoms. 1 mole of water molecules contains 6.022 into 10 to the power 23 water molecules, or 1 mole of sodium chloride equals 6.022 into 10 to the power 23 formula units of sodium chloride. Having defined the mole, it is now easier to know the mass of 1 mole of substance or constituent entities. The mass of 1 mole of substance in gram is called its molar mass. The molar mass in gram is numerically equal to atomic or molecular or molar mass in unit. Molar mass of water equals 18.02 gram per mole. Molar mass of sodium chloride equals 58.5 gram per mole. 1.9 percentage composition. So far we were dealing with number of entities present in a given sample, but many a time information regarding the percentage of a particular element present in a compound is required. Suppose an unknown or new compound is given to you. The first question you would ask is what is the formula, or what are its constituent, or in what ratio they are present in the given compound. For known compounds also, such information provides check whether the given sample contains same percentage of element as present in the pure sample. In other words, one can check the purity of a given sample by analyzing this data. Let us understand it by taking the example of water, that is H2O. Since water contains hydrogen and oxygen, the percentage composition of both these elements can be calculated as mass percent of an element equals mass of that element in compound into 100 upon mass of the compound. Molar mass of water equals 18.02 gram. Mass percentage of hydrogen equals 2 into 1.008 upon 18.02 into 100 equals 11.18%. Mass percent of oxygen equals 16.00 upon 18.02 into 100 equals 88.79%. Let us take one more example. What is the percentage of carbon, hydrogen and oxygen in ethanol? Molecular mass of ethanol is C2H5OH. Molar mass of ethanol equals 2 into 12.01 plus 6 into 1.008 plus 16.00 gram equals 46.068 gram. Mass percentage of carbon equals 24.02 upon 46.068 into 100 equals 52.14%. Similarly, the mass percent of hydrogen equals 13.13%. Mass percent of oxygen equals 34.73%. After understanding the calculation of percentage of mass, let us now see what the information can be obtained from the percentage composition data. 1.9.1 Empirical formula or molecular formula. An empirical formula represents the simplest whole number ratio of various atoms present in a compound, whereas the molecular formula shows the exact number of different types of atoms present in a molecule of a compound. If the mass percent of various elements present in compound is known, its empirical formula can be determined. Molecular formula can be further obtained if the molar mass is known. The following example illustrates the sequence. Problem 1.2. A compound contains 4.07% of hydrogen, 24.27% of carbon and 71.65% of chlorine. Its molar mass is 98.96 gram. What are its empirical and molecular formulas? Solution. Step 1. Conversion of mass percent to grams. Since we are having mass percent, it can be convenient to use 100 gram of compound as the starting material. Thus, in 100 gram sample of above compound, 4.07 gram is hydrogen, 24.27 gram is carbon and 71.65 gram chlorine are present. Step 2. Convert the number of moles of each element. Divide the masses obtained above by respective atomic masses of various elements. This gives the number of moles of constituent element in the compound. Moles of hydrogen equals 4.07 gram upon 1.008 gram equals 4.04. Similarly, moles of carbon equals 2.021 and moles of chlorine equals 2.021. Step 3. Divide each of the moles values obtained from above data by the smallest number amongst them. Since 2.021 is the smallest value, division by it gives the ratio of 2:1:1 or hydrogen is to carbon is to chlorine. In the case if it is not a whole number, then they may be converted into whole number by multiplying the suitable coefficient. Step 4. Write down the empirical formula by mentioning the number after writing the symbols of respective elements. CH2Cl is thus the empirical formula of the above compound. Step 5. Writing molecular formula. A. Determine empirical formula by adding the atomic mass of various atoms present in the empirical formula. For CH2Cl, empirical formula mass is 12.01 plus 2 into 1.008 plus 35.453 gram equal 49.48 gram. B. Divide the molar mass by empirical formula mass. Molar mass upon empirical formula mass equals 98.96 gram upon 49.48 gram equals 2. So N equals 2. Multiply the empirical formula by N obtained above to get the molecular formula. Empirical formula equals CH2Cl and N equals 2. Hence the molecular formula equals C2H4 and Cl2. 1.10. Stoichiometry and stoichiometric calculation. The word stoichiometry is derived from two Greek words, stoichiochion meaning element and metron meaning measure. Stoichiometry thus deals with the calculation of masses, sometimes volume also, of the reactants and the products involved in the chemical reaction. Before understanding how to calculate the amount of reactants required or the products produced in a chemical reaction, let us study what information is available for balanced chemical equation of a given reaction. Let us consider the combustion of methane. A balanced equation for this reaction is given as below. CH4 plus 2O2 gives CO2 plus 2H2O. Here methane and dioxygen are called reactants and carbon dioxide and water are called products. Note that all reactants and the products are gases in the above reaction, and this has been indicated by letter G in the brackets next to its formula. Similarly, in case of solids or liquids, S and I are written respectively. The coefficient 2,4O2 and H2O are called stoichiometric coefficient. Similarly, the coefficient for CH4 and CO2 is 1 in each case. They represent the number of molecules and moles as well taking part in the reaction or formed in the reaction. Thus, according to the above chemical reaction, 1 mole of CH4 gas reacts to 2 mole of O2 gas to give 1 mole of CO2 and 2 moles of H2O. 1 molecule of CH4 gas reacts with 2 molecules of O2 to give 1 molecule of CO2 gas and 2 molecules of H2O gas, or 22.7 liter of CH4 reacts with 45.4 liter of O2 to give 22.7 liter of carbon dioxide and 45.4 liter of H2O, or 16 gram of CH4 reacts with 2 into 32 gram of O2 to give 44 gram of CO2 and 2 into 18 gram of H2O. From the above relationships, the given data can be interconverted as follows: mass, moles and number of molecules. Mass upon volume equals density. 1.10.1 Limiting reagent. Many a time reactions are carried out with the amounts of reactants that are different than the amount as required by balanced chemical reaction. In such situation, one reactant is in more amount than amount required by balanced chemical reaction. The reactant which is present in least amount get consumed after some time, and after that further reaction does not take place whatever be the amount of the other reactant. Hence the reactant which get consumed first limits the amount of product formed and is therefore called limiting reagent. In performing stoichiometric calculation, this aspect is also kept in mind. 1.10.2 Reactions in solution. A majority of reactions in laboratories are carried out in solution. Therefore, it is important to understand as how the amount of substance is expressed when it is present in the solution. The concentration of the solution or amount of substance present in its given volume can be expressed in any of the following ways. Number 1, mass percent or weight percent or W upon W percent. Number 2, mole fraction. Number 3, molarity. Number 4, molality. Let us now understand each one of them in detail. Balancing a chemical equation. According to the law of conservation of mass, a balanced chemical equation has the same number of atoms of each element on both sides of the equation. Many chemical equations can be balanced by trial and error. Let us take the reactants of a few metals and non-metals with oxygen to gives oxide. 4Fe plus 3O2 gives 2Fe2O3 is the balanced equation, while P4 plus O2 gives P4O10 is an unbalanced equation. Equation A and B are balanced since there are same number of metal and oxygen atoms on each side of the equation. However, equation C is not balanced. In this equation, phosphorus atoms are balanced but not the oxygen atoms. To balance it, we must place the coefficient 5 on the left side of equation or on the left side of the equation to balance the oxygen atoms appearing on the right side of the equation. P4 solid plus 5O2 gas gives P4O10. This is the balanced equation. Now let us take the combustion of propane C3H8. This equation can be balanced in these steps. Write down the correct formulas of reactants and products. Here propane and oxygen are reactants and the carbon dioxide and water are products. C3H8 plus O2 gives CO2 plus H2O. This is an unbalanced reaction. Balance the number of carbons. Since 3 carbon atoms are in the reactant side, therefore 3 CO2 molecules are required on the right side. C3H8 plus O2 gives 3 CO2 plus H2O. Balance the number of hydrogen. Balance the number of oxygen. Step 5 is to verify the number of atoms of each element is balanced in the final equation. The equation shows 3 carbon atoms, 8 hydrogen atoms and 10 oxygen atoms on each side. All equations that have correct formulas for all reactants and products can be balanced. Always remember that subscripts in the formula of reactants and products cannot be changed to balance an equation. Now here is 3 problems, problem 1.3, 1.4 and 1.5. Pause the video and just solve it. Number 1 is mass percent. It is obtained by using the following reaction. Mass percent equals mass of solute upon mass of solution into 100. Here is problem 1.6. Just solve it. Number 2 is mole fraction. It is the ratio of number of moles of a particular component to the total number of moles of the solution. If a substance A dissolves in substance B and their number of moles are Na and Nb respectively, then the mole fractions of A and B are given by mole fraction of A equals number of mole of A upon number of moles of solutions equals Na upon Na plus Nb. Mole fraction of B equals Nb upon Na plus Nb. Number 3 is molarity. It is most widely used unit and is denoted by capital M. It is defined as number of moles of the solute in 1 liter of the solution. Thus, molarity equals number of moles of solute upon volume of solutions in liter. Suppose we have 1 molar solution of a substance, say NaOH or sodium hydroxide, and we want to prepare 0.2 molar solution from it. 1 molarity of NaOH means 1 mole of NaOH present in 1 liter of solution. For 0.2 molarity solution, we required 0.2 mole of NaOH dissolved in 1 liter of solution. Hence, for making 0.2 molarity solution of 1 molarity solution, we have to take account into the volume of 1 molarity of NaOH solution which contains 0.2 mole of NaOH and dilute the solution with water to 1 liter. Now, how much the volume of concentrated 1 molarity NaOH solution be taken which contains 0.2 moles of NaOH can be calculated as follows. If 1 mole is present in 1 liter of 1000 ml solution, then 0.2 mole is present in 1000 ml upon 1 mole into 0.2 mole solution equals 200 milliliter solution. Thus 200 milliliter of 1 molar NaOH are taken and enough water is added to dilute it to make 1 liter. In fact, for such calculation, a general formula M1V1 equals M2V2 where M and V are molarity and volume respectively can be used. In this case, M1 is equal to 0.2 molarity and V1 is equal to 1000 ml and M2 equals 1.0 m and V2 is to be calculated. Substituting the value in this formula, we get V2 equals 0.2 into 1000 upon 1. equals 200 liter. Note that the number of moles of solute, that is NaOH, was 0.2 in 200 ml and it has remained the same, that is 0.2, even after dilution in 1000 ml, as we have changed just the amount of solvent, that is water, and have not done anything with respect to NaOH, but keep in mind the concentration. Now here is one problem 1.7. Pause the video and solve it. Number 4 is molality. It is defined as the number of moles of solute present in 1 kg of solvent. It is denoted by small m. Thus, molality equals number of moles of solute upon mass of solvent in kg. Now here is the problem 1.8. Pause the video and solve it. Summary. Chemistry as we understand it today is not a very old discipline. People in ancient India already had knowledge of many scientific phenomena much before the advent of modern science. They applied the knowledge of chemistry in various walks of life. The study of chemistry is very important as its domain encompasses every sphere of life. Chemists study the properties and structure of substances and the changes undergone by them. All substances contain matter which can exist in 3 states: solid, liquid and gas. The constituent particles are held together in different ways in the states of matter and they exhibit their characteristic property. Matter can be also classified into elements, compounds and mixture. An element contains particles of only one type, which may be atoms or molecules. The compound are formed where atoms of 2 or more elements combine in a fixed ratio to each other. Mixture occur widely and many of the substances present around us are mixtures. When the properties of these substances are studied, measurement is inherent. The quantification of properties requires a system of measurement and unit in which the quantities are to be expressed. Many systems of measurement exist, of which the English and the metric systems are widely used. The scientific community, however, has agreed to a uniform and common system throughout the world, which is abbreviated as SI units or International System of Units. Since measurement involves recording of data which are always associated with a certain amount of uncertainty, the proper handling of data obtained by measuring the quantities is very important. The measurement of quantities in chemistry are spread over a wide range of 10 inverse 31 to 10 to the power 23. Hence, a convenient system of expressing the number in scientific notation is used. The uncertainty is taken care of by specifying the number of significant figures in which the observations are recorded. The dimensional analysis helps us to express the measured quantities in different system of units. Hence, it is possible to interconvert the results from one system of units to another. The combination of different atoms is governed by basic law of chemical composition, these being the law of conservation of mass, law of definite proportion, law of multiple proportion, Gay-Lussac law of gaseous volumes and Avogadro's law. All these laws led to the Dalton's atomic theory, which stated the atoms are building blocks of matter. The atomic mass of an element is expressed to the relative to C12 isotope of carbon, which has an exact value of 12 units. Usually, the atomic mass used for an element is the average atomic mass obtained by taking into account the natural abundance of different isotopes of that element. The molecular mass of a molecule is obtained by taking sum of atomic masses of different atoms present in the molecule. The molecular formula can be calculated by determining the mass percent of different element present in a compound and its molecular mass. The number of atoms, molecules or any other particles present in a given system are expressed in terms of Avogadro's constant, which is 6.022 into 10 to the power 23. This is known as 1 mole of respective particles or entities. Chemical reaction represent the chemical changes undergone by different element and compound. A balanced chemical equation provides a lot of information. The coefficient indicate the molar ratios and the respective number of particles taking part in that particular reaction. The quantitative study of the reactants required or products formed is called stoichiometry. Using stoichiometrical calculations, the amount of one or more reactants required to produce a particular amount of product can be determined and vice versa. The amount of substance present in a given volume of solution is expressed in number of ways. Example, mass percent, mole fraction, molarity or